So it makes me especially happy to introduce Annie, Anirudha Majumdar, who is an assistant professor at the Department of Mechanical and Aerospace Engineering at Princeton University. And he doubles as a visiting researcher at the new Google AI lab at Princeton. And Annie says that actually it's closer to his home than his actual office at Princeton, which is, as we know, it's a bit risky. it's dangerous. Anyway, so as you probably all know, or most of you know, Annie, it wasn't that long ago that he was at MIT. He graduated in 2016 and then spent a year at Stanford. And now he's leading a lab at Princeton University. And his research is on sort of focused on providing or understanding how or when or to what degree we can provide guarantees or evaluate risk in robotic systems that are highly dynamical or that have rich sensory input, or even that are sort of captured, modeled by complex but very powerful computational architectures like neural networks. And if you go through his bio, one of the achievements that clearly stands out is that in 2018, he was awarded the best paper of the year at the International Journal of Robotics Research, which, like as we all know, right, as a community, we are probably producing, I don't know, in the order of 100,000 papers or contributions, 100,000 contributions per year. And standing to the top of that gigantic number with all the noise that comes is something quite unique, right? So I think that that's something that should be acknowledged. And one of the interesting things is that that paper, sort of the focus of that paper is obviously funnels or family of funnels for real-time feedback motion control. And that emphasis on robustness is something that it's still there, right? That's still at the core of what Annie is interested in. So that hasn't changed. But that paper or that line of research didn't have neural networks in there. Mm-hmm. So clearly something has changed there. Yep. So it'd be great to know more about it.
Sounds good.
Thank you for coming.
Thank you. Thank you very much, Alberto, for the very generous introduction. So I'm really excited to be back here. So today I'll tell you about some of the research we've been doing in my group on making safety and generalization guarantees for learning-based control of robotic systems. So the main question we've been thinking about is this really fundamental problem of generalization. So let's say you have an unmanned aerial vehicle, a UAV, and you test it out in 1,000 different environments. So many tests, and you find that the robot does pretty well. So the question that we're interested in is what happens when you place this robot in some new environment, so some 1,001st environment that you've never encountered before. So how can we make guarantees on the success of your system in some novel environment, maybe with some high probability? So this problem of generalization is really ubiquitous across robotics applications. So if you think about training a neural network policy for manipulation, you might train it on a very large data set of objects. But really the question you're interested in is what happens when I give it some new object that was not part of my training data? How can I say with some high confidence that control policy learned from some finite amount of data will generalize to a novel object? So there are a number of really fundamental technical challenges associated with this. So first is the dynamics of the system itself could potentially be nonlinear, could potentially also be hybrid. Also, the environment geometry is not known to the robot a priori. So I'm using the word environment kind of broadly here. So if you think about navigation or obstacle avoidance, you can think about the environment corresponding to obstacles. But if you're thinking about manipulation, then the environment could correspond to objects that the robot is going to manipulate. We also have rich sensing modalities, which is nice from a practical perspective, but from a theoretical perspective makes things often very challenging. So if your control policies are just based on visual inputs or depth inputs, it's hard to say formal things. And finally, we have some kinds of like learning in the loop. So potentially your control policies could have neural networks in them, and that again makes it hard to make any guarantees on generalization. So there's a lot of related work addressing many of these technical challenges. So a lot of work in robust control, reachability, funnels, chance-constrained programming tries to address the challenge of uncertainty in the dynamics or even nonlinear or hybrid dynamics. So while these approaches are extremely powerful, they typically require some kind of explicit model of uncertainty affecting your system. So for robust control or reachability, this might take the form of some set of worst-case disturbances that your system might encounter. Or for chance-constrained programming, you might want some generative model, so a probability distribution over the uncertainty that affects your system. And I think writing down explicit models of uncertainty for environments is a really challenging task, and getting that exactly right is pretty challenging. So think about how you might do that for how you might write down an explicit generative model for all objects that your robotic manipulator might encounter. So one way to deal with environments that are unknown a priori is to do real-time planning, to do receding horizon control. And you can make safety guarantees on these kinds of schemes by either assuming that you have some emergency maneuver, like a stopping maneuver or a loiter circle that you can deploy to keep your robot safe. Or you could make some assumptions on the geometry of the environment. So if you're thinking about navigation, then you could assume that obstacles in the environment are always separated by some threshold. And you can then say that you'll continue to navigate without any collisions, and that gives you a guarantee with probability 1. But I think often these kinds of geometric conditions are difficult to write down. They can be pretty restrictive. And asking for a guarantee with probability 1 that your robot will always succeed or will not crash, I think that's often too much to ask for. And making probabilistic guarantees instead is the way to go, especially when you have rich sensing modalities like vision or depth that can be inherently noisy. So one way to make probabilistic guarantees is to pose everything as a POMDP, where you think of the environment as being part of your partially observable state. So I guess the simplest way to do this gets pretty computationally interactable very quickly. So you're often forced to make certain approximations or assumptions, which then makes it hard to talk about generalization. So the approach that I'll talk about today tries to address some of these challenges. So we want to make generalization guarantees on systems that have nonlinear dynamics, rich sensing modalities, and potentially neural network-based architectures as well. Okay, so let me first state the formal kind of problem statement, and then I'll describe the approach. So I'll assume that your system has some dynamics. So X is the state, U is the control input, E is the environment that the robot is operating in. And the main assumption that I'll make, at least for now, so I'll relax this a little bit later, but the main assumption will be that there's some true distribution from which your environments are being drawn, but that this distribution is not known to us. But we have some finite number of examples that are drawn IID from this true but unknown distribution over environments. So if your robot has some sensor, potentially a rich sensing modality like vision or depth, the goal is to design a control policy, so just mappings from sensor measurements to control inputs that will try to minimize some cost. So the cost here, so C pi E is the cost of policy pi when executed on environment E. So I'll assume that the costs are bounded, and without further loss of generality, I'll assume that they're bounded between 0 and 1. And the final assumption is that for any policy pi, we can evaluate the cost for that policy on our training environment. So we can run any given policy on our training environments and see what the costs are for just the training environments in S. So our goal then is to synthesize a control policy that minimizes the expected cost across environments. And actually, we'll work with a slightly more general formulation where instead of choosing a specific policy pi, we'll choose a distribution over policies to minimize the expected cost across environments. So I'll talk about why this general formulation is a little bit more helpful. So this inner expectation is because of stochasticity in how you're picking the policy from this distribution P. And this outer expectation is the main challenge here, which is that this distribution from which environments are being drawn, that distribution is not known to us. We only have indirect access to it in the form of a finite number of examples. And so P is the thing we're trying to choose in order to ideally minimize this expectation. Okay, so the key technical idea behind our approach is to use some theory from generalization theory, which has primarily been developed in theoretical machine learning in the supervised learning context. And the main kind of technical contribution, the main technical hurdle is in taking these theorems, these powerful results from supervised learning and translating them to our policy learning settings via a reduction-based approach. So what this will allow us to do is come up with upper bounds on the expected cost across environments. So upper bounds on the quantity that we care about minimizing. And then the algorithmic approach is basically to find policies or distributions over policies that minimize this upper bound. So we'll be able to do this using convex optimization in certain settings and using stochastic gradient descent in more generic settings. So the specific generalization framework we'll use is called PAC-Bayes theory. So again, PAC-Bayes theory, most of the development has been in supervised learning. And they provide some of the tightest known generalization bounds for classical supervised learning approaches like support vector machines. And more recently, so for the last 2 years or so, there's been a lot of excitement around PAC-Bayes because they seem to be promising in terms of explaining or promoting generalization for deep neural networks. And there's been kind of like a resurgence of interest in this area recently. So if you haven't seen PAC-Bayes theory before, so I want to make sure that you go away from the talk with at least knowing what the main kind of result is from PAC-Bayes. So I'll first describe it in the supervised learning context, and then I'll talk about how to translate that to our policy learning setting. So in the supervised learning setting, we have some input space. So maybe think about the space of all images. And we have some label space. So these could be object categories. And again, we'll assume that there's some true but unknown distribution from which images are being drawn in the real world. And we have some hypothesis class. So maybe think about neural networks with some given architecture parameterized by weights W. And we have some loss function that tells us how a hypothesis does on any given example. And PAC-Bayes theory will basically apply to learning algorithms that have this following very general structure. So the first thing we're going to do before seeing any data whatsoever is we're going to pick a prior, so a probability distribution over our hypothesis space. We then observe some training data, so some data samples drawn from this unknown distribution. And then we'll choose a posterior distribution based on our training data and potentially based on the prior as well. So one important thing to point out here is that the prior and the posterior don't have to necessarily be the Bayesian like prior and posterior, so you don't have to do exact Bayesian inference or anything like that. So you can if you want to, but the bounds I'll show hold for any prior and posterior. Okay, so let's define our training loss. So this is the loss of a distribution over hypotheses on our training samples. So this inner expectation is because, again, we're choosing distributions over hypotheses. And this is the true expected loss. So this is the thing that we really want to minimize. And this is the main result from PAC-Bayes theory in the supervised learning context. So the theorem says that with probability 1 minus delta over the sampling of your training data, so delta is some parameter that you can set, this following upper bound holds. So we can upper bound the true expected loss, so the quantity that we care about, in terms of the training loss, which we can evaluate, plus this extra term that sort of looks like a regularizer. And the main term here is the scale divergence between your posterior and the prior. So this regularizer is kind of trying to keep your posterior from moving too far away in the KL sense from your prior. So this upper bound, so this gives us a guarantee on the true expected loss, so on the quantity that we care about. Okay, so I'll pause here maybe for a second and just make sure everyone is on the same page with at least what the result is from PAC-Bayes. Question, yeah?
I see this equation similar to the statistical learning theory generalization bound.
Absolutely, yeah.
Is there a VC dimension or the shattering coefficient
Yeah.
for the regularizer term? And
Yes.
So, how I don't see the shattering coefficient as a trivial thing to calculate. So is it estimated? Is it really calculated?
No, so I guess that's one of the nice things about the PAC-Bayes bounds. So the PAC-Bayes bounds are a little bit more like recent than the VC like dimension type bounds. So there were older bounds like before PAC-Bayes where it had a similar structure, but this extra term was somehow based on the complexity of the hypothesis class that you were considering. And those things are typically very challenging to compute, or at least get tight approximations for. So that's one of the nice things here is that you don't need to compute things that are, compute things like the fat shattering like dimension or the VC dimension. Yeah, of course.
So this PAC-Bayes theory is not, the statistical learning theory is a pessimistic way, getting the worst case. Does this theory get the same approach?
Worst case over?
Of the difference between expected loss and empirical loss overcome a certain epsilon, like as in the worst case, I would still have a learning guarantee.
Yeah, I guess there isn't really a sense of worst case here. So this quantity is the expectation. So this is the training loss, sorry, and this quantity is the expected value. So it's still like expectation. It's not really like worst case. It's not. There's no like adversary here. All the data are being drawn from this IID, from this true but unknown distribution. Okay. So yeah. Sorry, Lucas, go ahead.
What can P0 depend on? Like, if I change the loss function, do I have to stick to the same P0 to get this bound, or what is allowed to?
Good. Yeah. So P0. So the way I think about it is that it's encoding some kind of domain knowledge that you have, like as an engineer, maybe. So if you have some probability distribution that you think kind of approximately describes your environments, you can use that to induce a prior over control policies. So I see that as like baking in like domain knowledge that you have. Okay, so the key kind of technical idea is to translate these generalization bounds from supervised learning to our policy learning setting. So again, in the supervised learning setting, we have some input. We have a hypothesis that takes the input, maps to a label. We have some loss function, and PAC-Bayes allows us to get an upper bound on the true expected cost on new input data. So we're basically going to map our policy learning setting onto the supervised learning setting. So this is a reduction in the formal sense. So we're going to think about the environment as corresponding to the input. We'll think about the policy essentially as corresponding to the hypothesis. So policy takes in an environment and maps it to a control action via sensor measurements. We have our cost function, and PAC-Bayes theory then allows us to make a guarantee on the expected cost of policies or distributions over policies on new environments. So there are, of course, some details that I'm hiding here. So there's a temporal aspect to these problems. It's not just a single decision. But this is kind of the high-level idea behind the mapping or the reduction from policy learning to supervised learning. And this allows us to essentially translate the PAC-Bayes bound from supervised learning onto the policy learning setting. So this is what we end up with. So again, if we define our training cost as the cost of some distribution over policies P on just the training environments, this again is the quantity we're trying to minimize. Then again, we have a bound, so an upper bound on the true expected cost as a summation of the training cost plus this regularization term. So the idea then is to take this bound and kind of use it as part of an algorithm. So the algorithmic approach will be to find a distribution over policies P that minimizes this upper bound that comes from PAC-Bayes. Dima? So here the costs are really assigned with respect to trajectory, like entire trajectories. So that temporal aspect is something I was like hiding here. So on your training data set, you can, right? So that's the assumption that you can evaluate the cost, at least on your training environments. So yeah, so the algorithmic approach is to find a policy distribution, so distribution over policies that minimizes this upper bound. So for certain settings, so when you're optimizing over just a finite policy space, you can do this via convex optimization. And for more general settings where you have a policy class, maybe with parameterized neural networks with weights, then we can use something more generic like stochastic gradient descent. So I'll talk about the first case first. So suppose we have some finite set of policies. Our goal is to find a discrete probability vector P in order to minimize this PAC-Bayes bound. So minimizing the PAC-Bayes bound corresponds to this optimization problem. So this thing is the training cost, and this is the regularizer. And the constraints are just saying that we have a valid discrete probability vector. So yeah, it turns out that you can tackle this using convex optimization, and in particular using relative entropy programming, which is a kind of fairly recently studied class of convex optimization problems, which have roots going back a couple of decades. But the main kind of constraint that it can handle is this. So if we have three decision variables, mu, nu, and lambda, so let's say mu and nu are probability vectors, lambda is a scalar decision variable, then we can impose the condition that the KL divergence between mu and nu is less than or equal to lambda. And we can also handle linear equality and inequality constraints. And the objective has to be linear in our decision variables. So that's the general kind of form of a relative entropy program. And you can solve these reasonably efficiently via interior point methods. And there are a number of solvers out there that now allow you to specify these REPs and be able to solve them. So if you're wondering how these relative entropy programs compare to other classes of convex optimization problems that you might be more familiar with, so linear programs, second-order cone programs, geometric programs. So it turns out relative entropy programs are a superclass, so they have all of these as special cases. And there's also an interesting relationship to semi-definite programs. So it's easy to show that relative entropy programs contain things that you cannot write directly with semi-definite programs. What's not known, at least last time I checked, is the converse. So whether there are things that you can express with semi-definite programs that you can't directly express with relative entropy programs. So either the picture looks sort of like this, or it looks like this. But either way, relative entropy programs are a pretty general and interesting class of convex optimization problems that are still reasonably tractable. Okay, so yeah, this was our optimization problem. So the main kind of difficulty here is this KL divergence term. So you can take this problem and massage it into a form that sort of looks like a relative entropy program with some details. But essentially, we can solve this using solve this to like global optimality using relative entropy programming. Okay, so that's the finite case, so finite policy case. So in the more general setting where we have continuously parameterized policies, so for example, neural networks, again, we have to specify distributions over our policies. And we do that by specifying distributions over the weights, just like Gaussians, for example. So we choose a mu and a diagonal covariance matrix, and that defines the distribution. Lucas?
Just a question. So you're always solving for a distribution over policies?
Yes.
Like if I was actually to deploy this, I have to draw a policy from my set and then run it?
Correct, yeah.
How much, if you go back to the bound in the green space, if
Sure.
I just say I'm going to pick one policy, so P is either 0 or 1,
Yeah.
how much worse is it?
So in the discrete setting, it's actually not too bad because I mean, you lose a little bit because the KL divergence will be larger. But in principle, you can do it and you'll get something. In the continuous setting, it's a little bit more difficult, right? Because the KL divergence term will blow up if you ask for like a Dirac like delta that you're optimizing. Yeah. So you do lose like a little bit, yeah. So you can compute the KL divergence between Gaussians in closed form. And essentially, the idea is to find a mu and a S, mean and a covariance, that minimizes the bound that we obtain using PAC-Bayes via stochastic gradient descent. So there's one technical difficulty here, which is that in order to evaluate the training cost, there's this expectation over policies. So we kind of resolve this just via sampling and using some concentration inequalities. So this is similar to an approach from Zugate and Roy, where they were using PAC-Bayes to come up with generalization bounds for neural networks. Okay, so I'll talk about some results next. So we applied this on a couple of different problems. So the first one is an obstacle avoidance problem. So this is a ground vehicle model with a range sensor, giving it distances along 20 different directions. So we simulated this using PyBullet. And the goal is to learn a reactive obstacle avoidance controller. So we'll parameterize our policies in a very simple form. It's just a linear combination of 1 over the depth. So these kinds of really simple reactive control policies often work very well in practice, but they're often very hard to make guarantees on and to say anything about generalization to environments that you haven't tested them out on. So these are some examples of the learned policy on novel environments. So we picked some finite number of training environments, minimized the PAC-Bayes bound, and this is the policy being deployed on new environments. So you'll see it crash at some point, but yeah, for the most part, it seems to do well. Yeah, so that one, it just crashed. Yeah. So here are the numerical results. So the top row is showing the number of examples we use for training. The middle row is the bound that we obtain using PAC-Bayes. And the bottom row is the true estimated success rate just by exhaustively sampling, just running the policy on lots and lots of test environments. So as you can see, even with a relatively small number of training environments, the bounds that we're getting are pretty tight. And as you increase the number of training environments, the bounds get even tighter. So the next example was a little bit more challenging. So the goal here was to demonstrate that we're able to get some strong guarantees on generalization for neural network-based control policies. So we simulated the system using PyBullet. So we had a RGBD sensor that was simulated, and that's what the control policies depend on. Lucas?
Just a question on the cars thing.
Yeah.
For each environment, you can roll out as many times as you want in
Yeah.
that environment from different initial conditions and everything?
Yeah, so I guess the way I think about initial conditions is that you can think of it as just being part of your environment. So yeah, that stochasticity you can just say is like part of my environment. Okay. Yeah. So we used 2,000 training objects from the ShapeNet data set to train neural network-based policies that where the input is the RGBD sensing. So these are some example objects from the ShapeNet data set. So we randomized masses, inertias, initial conditions. And this is the kind of high-level neural network architecture. So the first thing we're doing is just getting an estimate of the center of mass, so just the centroid of the object. And then we take our depth image, colorize it, so we can use a pre-trained neural network, VGG16, and then we pass that through a number of fully connected layers, and then basically combine the output of that neural network with the center of mass estimate. So just the centroid estimate. And these are the results on test objects. So we trained using 2,000 training objects, and this is on novel objects. So the bound we're able to get here is around 71% success rate on novel objects. And the empirical success rate, if you run the policy again on many test objects, is around 81%. So of course, there's still some work to do, but I think this was really exciting to be able to get reasonably strong generalization guarantees for neural network-based control policies, which has traditionally been very challenging to do. We're also in the process of implementing some of these ideas on hardware. So this is the Parrot swing. So it takes off vertically and kind of transitions to forward flight to fly quicker. So this is in a Vicon setup, but we have a depth sensor that we're simulating. So the control policy is only using the simulated depth sensor. And this is deploying a reactive obstacle avoidance policy kind of similar to the one I showed with the car example. This is just from a couple of days ago. So actually, Alec, who's doing the work for this, is in the room. So he happened to be here for an entirely different event. So yeah, these are just from 2 days ago. So this is the PAC-Bayes policy deployed on these environments. Okay, so one question I haven't addressed yet is what happens when your test distribution is different from your training distribution. So we assume that, that there's this true underlying distribution from which all environments are being drawn. So there's a lot of work on this in the supervised learning context, so in domain adaptation and in distribution robustness. So we'll do something kind of close to spirit to distributional robustness. So the setup here is that we have our training distribution D and a test distribution D prime. And we'll make some assumption about how these two distributions are related. So we don't know each of these, but we'll assume that there's some maybe KL divergence bound between the two distributions. And you can generalize this to other divergences like the F divergence or Wasserstein distances. So the key kind of like technical idea is to use this Donsker rather than change of measure formula. What this says is that it allows you to bound the expectation of some random variable, so the cost in our setting, where the expectation is taken with respect to D prime, so the test distribution, in terms of the KL divergence between test and training, plus this term that sort of looks like an entropic risk metric. And this term depends only on the training distribution. So this term we assumed was bounded by B. And this other term we can bound directly using the PAC-Bayes bound that I presented before simply by working with exponentiated costs instead of the costs, and then you take the log of the bound. So this gives us a bound on the expected cost on the test environments. So we applied this again on this obstacle avoidance example. So here the training and test distributions differed in how the radii of the obstacles were sampled. So the blue is the training, the red or orange is the test. And I guess the key point here is that the test distribution is harder than the training one, in the sense that during training you see lots of environments where obstacles have a small radius, and then at test time you see more environments with larger obstacles. And these are the numerical results. So again, the top row is the number of training environments we're using. The middle row is the bound that we get using this robust version of the bound. And as you can see here, the bounds are, again, reasonably tight, so not quite as tight as they were before, but still potentially useful in practice. Okay, so there's one really important, couple of really important challenges with these distributionally robust bounds. So first is that we make some assumption on the KL divergence between test and training that might be hard to obtain. And even if you can obtain it, the bound might be extremely large because this bound is on the KL divergence is taking into account variations in all features of the environment, including completely irrelevant ones. So if you think about obstacle avoidance, maybe at training time you see objects that have a certain color, and then at test time you see objects that have a different color. This KL divergence is going to need to take into account that variation in the distribution, whereas we know that really we shouldn't be, like our obstacle avoidance controller shouldn't be sensitive to the colors of the objects. So what I'll present next is an approach that tries to get at this challenge. So the main idea is to design perception and control algorithms that are task-driven in the sense that they're minimalistic, so they depend on only portions of the state that are actually relevant to the control task that you're trying to do. Russ? Sure.
Comparing the output feedback design without the regularization
Yeah.
with the regularization, even for your simple obstacle avoidance environment,
Sure.
do you feel like SGD is doing a good job finding a good K to the output feedback problem, which we expect to be bad and not convex?
Without regularization or with? Or?
The big question is,
Right.
does regularization somehow make SGD work better, or somehow, or is it still the hard output feedback problem sitting there?
I think it makes it better in the sense that like you're not overfitting, right? So that's what it's preventing. So it's preventing SGD from just overfitting to your training data. And actually, I guess one thing I didn't say I should have mentioned is that for the grasping example, we tried just doing the simple thing where you minimize the training loss on just minimize the training loss, so no regularization, no regularization whatsoever, no like dropout or anything. And there we see that you actually do like overfit, so the test error then becomes smaller. So I think that's what the regularizer is giving you. I mean, of course, at the end of the day, with or without the regularizer, there's still a non-convex optimization problem kind of buried in there. Yeah, and that's not something we're tackling. We're just tackling preventing the overfitting, or trying to prevent the overfitting. All right. Okay, so the next part, just to make sure we're kind of on the same page about what I mean by task-driven perception and control. So let's think about a concrete example. So let's say you want your robot to catch an object, so maybe a ball. So one way to do this is to write down the equations of motion for ballistic motion, to use your robot sensors to figure out the full state of the robot, the full state of the ball, and maybe to use some kind of trajectory optimization motion planner to generate a trajectory that will go and intercept the trajectory of the ball. So it turns out if you study how humans do this, so there's decades of studies on this problem or studying humans doing these kinds of tasks, and also dogs catching frisbees. So it turns out the strategy is extremely different from this full state estimation version. So it's something called the gaze heuristic, which basically amounts to fixing your gaze on the object and adjusting your speed to keep that gaze angle at a constant value. So you can convince yourself that as the ball is falling, in order to keep that gaze angle at a constant, you're forced to go and meet the trajectory of the object. So this is a much simpler strategy in the sense that you're not estimating your full state. You're only estimating and modulating the single variable, which is the gaze angle. And actually, it turns out that humans use this kind of heuristic strategy for more complicated decisions as well. So this is the US Airways flight that landed on the Hudson River. So this is a quote from the co-pilot. So he said, it's not so much a mathematical calculation as a visual one. So when you're flying, a point that you cannot reach will rise in your windshield, and a point that you're going to overfly will descend in your windshield. So what they did was they were trying to decide whether to land at LaGuardia Airport. They fixed their gaze on the control tower of LaGuardia, and they found that the tower was rising in the windshield, and then decided that they weren't going to make it. So our goal here is to automatically synthesize these kinds of heuristics, these kinds of task-driven or minimalistic representations that don't rely on estimating the full state of the system. So the approach that I'll sketch is slightly different setting from what I was talking about before. So here we'll work in a model-based setting. So I'll assume that we have some dynamics model of our system described as a Markov decision process. And the key technical kind of tool we use is the theory of information bottlenecks, which came originally from information theory. And our approach will have two phases. So there's an offline phase where we generate this task-driven representations. So we'll call these variables task-relevant variables or TRVs that essentially create a bottleneck between the full state of the system and the control actions. So these are the X bars of the TRVs. And then online, what we're going to do is only estimate the task-relevant variables using our sensors. So in the gaze example, the TRV kind of intuitively you can think of as corresponding to the gaze angle, and that could be significantly lower dimensional than the full state of the system. So more precisely, this is the optimization problem we solve offline. So given, again, a Markov decision process model of our system, we try to synthesize two mappings. So the first mapping is the mapping from the full state to the task-relevant variable. That's the QT. And then the second mapping is the policy, which depends. The control actions only depend on the task-relevant variable. And the objective here is to minimize the expected cost with this additional term, which is the mutual information between the state and the TRV. So intuitively, the mutual information captures how independent two random variables are. So this is trying to filter out portions of the state that are not relevant to the control task that we're trying to do. And then online, we forget about the full state. We use our sensor measurements to only estimate these task-relevant variables and deploy the control policy based on those estimates. So there are two potential advantages to doing this. So the first is computational efficiency. So if you think about the gaze example, the task relevant variable could be significantly lower dimensional, so one dimensional in the gaze example. And the second potential advantage is robustness. So the intuition here is that if you're filtering out a lot of portions of your state, then if you have uncertainty or noise that's affecting those portions that you filtered out, then your control policy doesn't depend on that, so you're kind of naturally robust to that. So I'll illustrate this with a simple example. So this is the lava problem. So here we have 5 states. The robot wants to get to the goal. There's a lava, so if it reaches the lava, then it's going to get stuck in the lava. And the robot has a noisy sensor which tells it its position, but it has some error of being wrong. So maybe the simplest thing you could do is kind of one based on the separation principle from control theory. So use your state estimator to figure out which state you're in, and then you look at the maximum likelihood estimate of the state, and then you apply a control action, assuming that is perfect. So you would apply this kind of policy. So if you estimated that your state was here, then you would go right. So the danger, of course, with this kind of approach is if you misestimate your state. So if you think that you're in state 2, but really you're in state 4, then you're going to go right, and you'll end up at the lava. So it turns out that, so actually this was nicely described in Pete Florence's master's thesis. And yeah, we found this to be a nice, simple example to test our intuitions on. So it turns out that if you apply this information bottleneck approach to try to generate a minimalistic policy in the sense that I described before, it actually comes up with an open loop strategy. So what it does is for the first 3 time step, it goes left, and then it goes right twice. So if you think about this, no matter where you start off initially, as long as you don't start off in the lava state, if you go left 3 times, at the end of that process, you'll end up at state 1, because if you try to go left from the wall, you'll still end up at state 1. And then you just go right twice. So this is purely open loop, and obviously very robust to sensing uncertainty because it's not using the sensor measurements at all. And if you compare this, so if you sample lots of different initial conditions and you apply the 2 policies, so you'll find that doing the maximum likelihood estimation and then taking an action based on that, so essentially assuming the separation principle, gives you a much higher variance of the costs as compared to this task-relevant strategy. So here's a slightly more complicated example. So this is a spring-loaded inverted pendulum. The goal here is to navigate to a specified location within 3 hops. And we computed the control policy using linearizations of the Poincare map, again using the information bottleneck approach. So in this case, the task-relevant variables that came out of the synthesis turns out to be just one-dimensional. So it took the 5-dimensional state, kind of compressed it down to some one-dimensional representation that was sufficient for doing this task, assuming that the initial conditions didn't vary too widely. And we compared this using an approach that estimates the full state of the system, so using ILQG. But the interesting thing here was that we compared it against 2 models of sensor noise. So the first model was the correct correct model of the sensor measurements. The second one had the covariance matrix for the sensor model incorrectly specified. And we compared what would happen if you deployed ILQG with the incorrect or the correct covariance and the task-relevant approach with the incorrect noise model. And what we found was that, so as you would expect, the ILQG strategy with the correct noise model does well. So this is a frequency of the histogram of the cumulative costs. But if you misspecify the noise model, ILQG is more sensitive to that misspecification than the task-relevant policy. And again, I think the intuition is that the task-relevant policy is filtering out lots of things. So if there's misspecification, uncertainty, noise in those portions that you're filtering out, then you're kind of naturally robust to that. So we're trying this out on some hardware implementation. So we have a ball catching robot that we had an undergrad and grad students build. So the goal would be to compare the policies that come out using our information bottleneck approach with something that does full state estimation and also comparing against the Bayes heuristic to see how we compare. Okay, so I just want to end with some directions for current and future work. So on the learning side, the generalization side, so one of the things we're thinking about is how to improve the bounds that we get. So the bounds are reasonably strong, but I think we can do a lot better by incorporating model-based priors. So if you have intuitions about your system or some priors about like physics, for example, you could potentially bake those in and get stronger generalization bounds. And we're also thinking about how to generalize to environments that are qualitatively different. The kinds of generalization I showed today are still don't require massively qualitatively different behavior at test time, but it would be nice if those kinds of things came out automatically of our formulations. We're also thinking about generalization bounds for imitation learning. So if you imagine learning some policy maybe from imperfect demonstrations, then you'd like to say something about the policy that you've learned on test environments where you didn't have demonstrations. And we're also thinking about the meta-learning setting where you're generalizing not just across different environments, but potentially across different tasks as well. We're also exploring generalization bounds beyond PAC-Bayes, so there's kind of a universe of bounds in supervised learning that we could potentially leverage. And finally, we're thinking about hardware implementation. So I presented some preliminary experiments today. We have a couple of other hardware platforms for manipulation and aerial manipulation that we're pretty excited about. On the task-driven perception and control side, so I think maybe the most exciting direction is to do active task-driven perception. So currently we're passively observing sensor measurements and using those to estimate our task-relevant variables. But you could imagine doing something similar to belief space planning where you do active task-driven perception. So you're taking actions that will reduce the uncertainty, but only in portions of the state that actually matter. And we're thinking about some other formulations as well using differential privacy. So yeah, I'll just end with some conclusions. So I presented some framework for making generalization guarantees via PAC-Bayes theory and some algorithms that implement this using convex optimization and stochastic gradient descent. So we're able to get some reasonably tight bounds on different examples, including policies that are based on neural networks. And I presented an approach for doing task-driven perception and control for getting computationally efficient and robust policies. So in general, I think there's a lot of really exciting potential for taking these tools in order to make guarantees on generalization and safety for learning-based control of robotic systems. So these are some papers. So actually, both Alec and Vince are around for a different meeting. So if you want to talk to them about any of this work, you should feel free to chat with them. And I'll just leave you with this contribution slide and take any further questions you have in the remaining time.
About the task-relevant variables, how complex is identifying both the map from the state to export the TRVs?
How complicated are they?
And finding a policy at the same time. So I don't understand what is the exact motivation for that. Is it just doing output feedback? Because what if your map from X to X bar is very dense? It's like 0.1, the first state, second state. It has all of them. So basically it means that you have to first measure all of the states, then have X bar, and then do the policy on basis.
Sure. Yeah, so the motivation is definitely like output feedback. So we want to filter out irrelevant portions of the state. So things that you don't want to be estimating at like real time, right? So if I'm like grasping this object, I don't care about the yaw like angle of the object because of the radial symmetry, so I want to like filter that out. So that's the motivation. And I guess the way we try to achieve that is through this mutual information term. So the mutual information is basically the thing that's trying to filter out irrelevant portions. So mutual information is like measuring how independent the full state is from the task relevant variables, and it's trying to make those as independent as possible.
across different, or environments starting from different distributions.
Yeah.
Could there be a way to have like a task relevant variable for distributions that could quantify, like you mentioned
That's
color?
yeah. I guess that's what I'm hoping. So we're not quite there yet. So yeah, what I'd like to do is to be able to like take like the task relevant like approach and kind of like port that over to the first thing that I talked about. So we're not quite there yet. So we have some formulations that seem to work in theory, but we can't quite implement in practice, or the other way around, things that seem to work in practice, but we can't quite prove things about. But that's definitely the motivation. That's what we like to do. Yeah.
Yeah, thank you for a great talk, by the way. So kind of like continue to the question. Like, I find it interesting like the role these task relevant variables could play for like understanding more the behaviors of systems. Is there any way in which like we can like obtain guarantees from any like behavior of the system through these variables, like in terms of control, convergence, etc.?
To get like robustness guarantees. Yeah, so we have some results on that. Basically the kinds of results are if your like estimator is wrong, so maybe you misspecified your sensor model. In those settings we can prove some like robustness bounds. Yeah, we have like a kind of like preliminary theorem in the paper that tries to do that. But yeah, the kind of like result is that if you have some distribution some model that you believe to be true, but then in reality it's different, then the task relevant approach will be more robust to the misspecified model.
I wanted to ask a question to use the opportunity. So in the first part of your talk, where you sort of focus on providing bounds, so I was trying to sort of understand exactly how do I map that to a problem where I can use it. And it seems to me that there's two key components, if I understand. So one is you have some way of encoding the task, which in that context, it was the environment. So you have a way to encode the environment, which in both cases was an image, if I remember.
So I guess that's the sensor measurement, but the environment I'm thinking about as the actual like environment, right? So you're not necessarily encoding that.
The network sees the environment as some form of sensor measurement.
Correct. Yes.
And then so. Both the prior and that encoding, I didn't see, or I don't know if you've done experiments or sort of what is the effect of different options on that, how you encode the environment or how you present the environment to the network, or which prior you use, how much you constrain the prior to the actual bounds.
Yeah. So the prior definitely has a important effect. I mean, I see that as an opportunity. So I feel like the prior is a way we can bake in kind of like engineering knowledge that we have.
So in one of those examples, I don't know, just the grasping one, or the like, how would you do that? How do you encode that engineering into
I see. Yeah. So the simplest thing that we did for the grasping one was just saying that the center of mass, like just going to the center of mass, is like and doing a grasp there is already like a decent like strategy. So you can have a prior distribution that assigns like high weights to the policy that simply like goes and to the center of mass of the object. So like things like that you can bake into the priors.
But how is that then? How does that then affect sort of the actual computation of the bound that you showed?
Okay. Yeah. So the bound. Let me just.
Like the prior is defined as a set, right? If I remember.
So the prior is a distribution,
Okay.
over your policies. So yeah, let me pull it up. So this is the bound. So the P0 is the prior distribution over your policy space. So it's a probability distribution over your policy space. So it affects the bound because what you're trying to find is a distribution P that minimizes this entire bound. So if your prior was like already good, then this term will not be too big. So the regularization term will not need to be too big in order to do well on your training data. So I guess that's where it comes into the optimization problem. Yeah, and on the representation side, So I guess I see the environment as not as an image. So the image is just the sensor measurement. So the environment plus the actual like state of the robot is giving you a sensor measurement, and that's what the robot needs to rely on in order to execute the policy. The main kind of like assumption, the two main assumptions were that you can evaluate the cost of a policy on a given environment. So you can do that if you have a simulator. You can run like policies on the simulator, or if you have like an ARM farm or like something like that, right? You can like actually do hardware experiments where you run policies on different objects. Yeah, so it's not really the sensor measurement, I think.
Okay. So if you had an environment distribution, but now your sensor measurement could generate different sensor reading, I don't know, there's occlusions, for example.
Yeah.
How is that handled? I'm just trying to sort of visualize.
Sure. Yeah, so it's handled kind of implicitly, right? So you're hoping that the neural network will learn to either like reason about the occlusions, or will somehow like will still do well.
Okay. Cool. Okay.
All right.
Any other questions? Sorry.
So on slide 41, you were discussing the generalization of Bayesian neural networks.
Yeah.
So maybe I misunderstood this part, but when you were mentioning that you parameterize the distributions as Gaussians on the Bayesian neural network, there's no guarantee that the output of the Bayesian neural network will be a sum of Gaussians unless the activations themselves are very loose. Like if it's a sigmoid or something else, you're going to warp these distributions.
Of course. Yeah.
So does this only hold for the case of radar activations, or no?
No. This holds. So we don't need the output to be a Gaussian, right? So what we care about is just defining a distribution over the policy space, which is
would act more like an ELBO bound. Yeah. Okay. Gotcha.
Yeah. So it's not the output; it's the distribution on the weights that we want to be Gaussian. Yeah.
Cool.
For the second part, did you guys try other measures of similarities between trajectories besides mutual information, or did you just kind of settle on mutual information? Or
Yeah, so far we've settled mostly on mutual information. We have looked at other formulations. So I think like differential privacy actually might be a nice like formulation. So like Vince and I have like thought a little bit about it. Yeah, so it's not quite mutual information, but it's something else. I mean the intuition is that you want your output, so your policy, the thing that the policy outputs, which is the actions, you want that to be kind of like private, like in the sense that you don't want it to depend too much on the specifics of the state. So you want to hide like part of the state. So that's the intuition. So yeah, we've definitely been looking at other formulations, but haven't been able to prove things about other formulations.
All right. So
All right. Thank you.